Okay, thank you. Thank you very much, and thank you for the invitation. Today I'm going to talk about chiral and democratic theories and partition function in these kind of theories. This talk will be based on my recent work and these two papers, one by Witten. I will try to explain part of this paper, very basic. And this paper by Beloff and Moore, which is the formal version of the formal mathematical version of the Witten's paper. Okay, let me start with some introduction and motivation. Why we need, or why we want to study chiral partition functions. One of them, the first one, which is actually one of the motivations of some of you, is in type 2B supergravity. We have 5-form self-dual field. And when we want to compute the partition function directly in 10D, if we apply this constraint naively to the partition function, we get that the action is zero, vanishes, if we apply this constraint. However, when you go to the reduced theory, you can compute the partition function without any problem. No? And the question is, can we compute directly the partition function in 10D? Apparently we can, but another motivation, or my motivation in this case, is related with M theory and related with the objects, with the charge objects that the theory contains, which are the M2 and M5 branes. And in the microscopic theory, these two objects, they coexist. You can have electric and magnetic objects at the same time, similar to the U1 Maxwell that you have. You can have electrons and monopoles. In M theory, you can say that these are electrons and these are monopoles. This is more or less the analogy. You can have both at the same time. And in the microscopic theory, in principle, and just in principle, you can compute the partition function, no? Or the expectation value of these objects. However, it is difficult to do it. And this is why we go to the quantum field theory or the effective theory. But the problem in the effective theory is that the effective classical theory is formulated only in terms of this A3 form, which is the one that couples to this, similar to the one form in the Maxwell theory. But there is no A6 fields to couple to the M5 brane. And one of the aims of this work is to formulate an effective quantum M theory version to have A6 and F7 at the same footing in order to couple with the M5 brane and compute the partition function or the expectation value of these fields. The expectation value of this object is similar to the expectation value of the Wilson loop. This is what I'm talking about.
So there is no democratic formulation for M theory yet?
There are democratic formulation of M theory. I will talk about this, and I will use one of them, the one that is adapted to this kind of calculation. But yeah, there are several formulations of democratic M theory. Okay. One of the main concepts here is this section of a line bundle. And don't worry, I'm going to present the definition and go through the mathematics of this concept. I want to present this concept with one example which is familiar for you, and using this example, you will understand the rest of the talk. I want to present the charge scalar. Usually we think about this complex charge scalar as a scalar. However, if we perform a gauge transformation, we see that this scalar transforms with this phase. So the question is, if this field is really a scalar, it should be invariant under any transformation. However, it transforms. This is why we are used to see this field as a scalar. It's not a scalar. In this case, it's called a section of a line bundle. This is basically the definition of this kind of object. You perform a transformation, and the new field, the transformed field, transform with this face. Because of this object now is a section of a line bundle. If you want to take the derivative of this object, you have to introduce a connection. This is usually in U1 Maxwell, U1 gauge theory. You introduce a connection, and because of introduce this connection transforming as a U1 field, now you can derive this field. And the derivation of this field, now the derivative transforms exactly as the original object you are working with. If in addition you have an equation that defines this field, you can solve this equation if you know you have some method to compute to solve the equation, and you find field. You find this phi field. However, if you are able to find another function which transforms exactly like this field, you can be completely sure that this new function will be a solution of this equation. It will be a solution using a different A, which in the usual physical, we say that we are working in a different gauge. But it will be a solution of this equation, as long as the new field leave invariant the F. And this is what a gauge transformation does. So these two functions will be related by the gauge transformation. This will be the central object of this talk, to show how the partition functions are computed using these ideas related with the scalar field. We will work in a different space. You will see in a few minutes, but the main idea is here, and this is more familiar for you. So let me start with the effective partition function of an M5 brane. This is what is in the paper by Witten. And this is the main motivation why we want to compute partition functions for Chiral theories. As I said, in the microscopic theory, we have an A3 and an A6. This is electric, and this electric has associated field strength and has associated this gauge transformation. We also have an A6 potential, which its field strength is more complicated because it contains this extra Chern-Simons term, and it has a more complicated gauge transformation. And similar to the Wilson loop I mentioned, you can have Wilson loops, let's say, to this kind of objects. So for the M2 brane, you can have this object. However, for the M5 brane, the situation is a bit different to the usual quantum field theory version. Why? Because naively you may say, okay, as similar to the A3, the Wilson for the M5 brane will be just the integral of A6. However, if you see the gauge transformation of the A6, if you take only this field, this is not gauge invariant. This is why you need to introduce one more field. This B2 field is a B2 that lives on the M5 brane only. It's not a field that propagates on space. It's a field that lives on the M5 brane. And now the question is, what is the observable in the effective theory? If I have this field living on the 5 brane, but I don't see this field from the bulk. I mean, in the usual space, I don't see this field. Okay, the answer to this question is you have to integrate out this field. By integrating out this field, you get the effective theory depending only on A6. And you can do that, just to integrate out the B field. This is the quadratic term in the action. And see what happened here. When you plot this object in the path integral, that you want to compute, you get this new expression. This object is gauge invariant by construction. This is gauge invariant. And this is the gauge invariant combination. You can see here that B2 transforms with lambda 2. However, A3 transforms with D lambda 2. So this is the gauge invariant combination. Oh, sorry.
So why do kinetic cavities like dB2 minus A3?
That's that because this is the coupling with the background field. This is basically the Vesuvino term in the N5 ring. This is the coupling with the background fields of the M theory. It looks like a covariant derivative, but it's not. It's just a coupling with the background. This is the gauge invariant combination. You can go back again.
On the N5 ring.
On the N, yes, exactly. See that A3 transform with D lambda 2 and B2 transform with lambda 2 without derivative. So when you go to this is the gauge invariant combination. This transform without derivative, but this puts a derivative, and this transforms with derivative. So this is the gauge invariant combination. So this term is gauge invariant. And then you can rewrite this term in this way, where this set here is given by this expression. Let me show you what is H3 here is this. And
you say you integrated out B2, but B2 is still there.
the integration, I'm integrating out. This is the path integral. This is the integration out of B2. No. Yeah, it's still there, but it's integrated. No? Now, yeah, it's there, but it's inside the integral. What is the problem with this kind of integrals? In principle, this is just a usual quadratic Gaussian integral, and we know from quantum field theory how to solve this kind of integrals. The point is that on the N5 brane, and because of the supersymmetry of the N5 brane, these new objects, this combination here satisfy this extra constraint. And this is because of the counting of the number of freedom on the N5 brane. So this is one of the problems, and because of this, we don't know how to solve this integral. We don't know how to solve, because if you plug this here, you get 0. So, you get H3 wedge H3, and because of these are odd P form, this is 0 basically. This is bad for this kind of calculation. In addition, there is one more point related with this integral, and while this term here is gauge invariant, because of what I already explained, this part here is not gauge invariant. But it's only this part here. Now, when this part combined with this, it's gauge invariant again. To see that this part and this part is basically this, this combination. And this is a gauge invariant combination. However, when you split the integral in these two terms, the product of these two terms is gauge invariant. However, this partition function by itself is not gauge invariant. And A6 doesn't play any role in this path integral. In principle, you are computing the path integral of an object which is not gauge invariant. You may say that this is a problem. Actually, this is not a problem. This is what we're going to use to solve this kind of path integral. Why? Because of this. If you look at the transformation of this object, or the transformation of set in the partition function, the transformation is like this. Or you can rewrite this transformation in a more familiar way like this. And see, this term here is similar to the one I presented at the beginning for the charge scalar. So in this case, you can view this object as a charge scalar. Now it's not a scalar anymore. It transforms when you perform a gauge transformation. So you can see that this is the phase of the transformation. And you can view 1/2 as the charge of the scalar. This is one of the motivations to introduce the concept of a line bundle for this kind of objects. How to compute this, I will tell you in the next few minutes, but before that, I want to explain one more partition function, which is the one that we will use along this talk. And this is the partition function of the chiral scalar. This is a theory in 2D, the one that presented. This one is a theory in 6D. This is a theory in 2D. In 2D that can be formulated or can be defined in this way. You have a usual Maxwell type action F1, wedge F1 with this Bianchi identity, and you have this extra constraint. By the way, sigma 2 is closed. This is important for this kind of calculation. Or locally, if you want, you can solve the Bianchi identity, and locally you can rewrite this as an exact form, introducing a scalar field. So this is the chiral theory. And this theory, with this constraint, you have similar problems as in the previous theory. If you use this constraint here, you get a zero action. The action vanishes. So the classical theory, what the classical theory does is you first take the variation of this, you get the equation of motion, and after that is that you impose the constraint. But when you go to the quantum, you don't know what to do with this constraint, the quantum version of this. And this is what, in this sense, we are going to proceed similar to the previous example for M5 range for this kind of theory. And I'm going to present this in these three steps. This recipe is the one I'm going to follow to extend the work, the idea to the calculation of the partition function of M theory, the whole M theory. So the first step is to identify, in this case, a zero form global. It doesn't have to be global, no? Zero form symmetry. In this case, this theory has this symmetry. And you see that with this zero form constant, you plug this here. This is a constant. This is the action. This invariant under this transformation. This is the first step in this construction, and these are the ones that I'm going to follow in the next construction. The second step, and similarly to the previous example, is you relax this condition. You relax this condition, but by relaxing this condition, now it's not a symmetry anymore of the action. And what you do is you introduce a one form to compensate the new symmetry of the new theory. This is a different theory. What I'm going to use this theory, actually, not this one, to compute the partition function of this theory. This is an auxiliary theory, and this is the third step. You have to introduce a deformation. And why I want to introduce a deformation? Because I want to have a non-gauge invariant action. And this is unusual. I know that this is very unusual. I want to have a non-gauge invariant action. This term is not gauge invariant. Well, this term is gauge invariant. This one here is not gauge invariant, similar to the previous example. But why I want to have a non-gauge invariant action? Because I want to build a section of a line bundle. Why? You will see why I want to build a section of a line bundle, because this is the main point about this construction. But by introducing this term, now you have a new auxiliary action which has invariant part and has this extra term which is not invariant. And in particular, this action satisfies this. This is important too. You see that if you kill this one form, you go back to the original action. You remove this term, you end up with the original action. And this is one of the important points, because now if you compute the partition function for this object and you evaluate the action at 0, you are computing the partition function of the original theory. The point is that we don't know how to compute the partition function for this new action, but we will use the fact that this partition function is a section of a line bundle. So let me put all the pieces together in this case. We want to compute, in this case, the two-dimensional case, similar to the six-dimensional case for the M5, we want to compute the partition function of the chiral theory with this condition, or at least with this classical condition. We don't know what to do in the quantum version of this theory with this, we don't know, with this condition.
So when you say you want to compute that chiral theory path integral with that condition,
No, not with that condition.
so
I want to compute the partition function of this, but I don't know what is the meaning of this condition for this partition function, because I cannot impose this condition
if
directly
you
here.
impose it, you get just one.
Exactly, exactly.
Then but then still, as you said, for M5 brain, we know that the field is like self-dual or something.
Yes.
So you know the theory must have self-dual field, considering the degrees of freedom are the same. You want to compute the path integral of such theory.
Yes.
But if you naively put that action in the path integral, you get one. So
Exactly.
nonsense.
Exactly.
So that's why you're thinking about this A added form.
Exactly. And you will see why. You will see in a few minutes. No, I don't know how to compute this path integral with this condition. I don't know what is the meaning of this condition for this path integral. Or if I apply this condition naively here, I can just impose this condition with the delta, no? The Dirac delta here. However, it will be zero, no? Because the integration will be restricted to this path, you get one here. And this is why we introduce this auxiliary action with this condition. We know that, at least we know that if we evaluate this at zero, we recover this original partition function, where this action is given by this. And something that I didn't say, but you see that this is similar to the previous action we have, no? If here, instead of T5, you put B2, and here A3, you get the similar action, and also here, you get A3 wedge DB2. So these two actions are similar, but this is a easier problem to. And the only information so far we have about this partition function is that this partition function is a section of a line bundle, or if you want, it's a charge scalar. This is the only information we have. Okay, we have these two information so far. As in the introduction, the charge scalar was described by one equation, and this equation is the one that defines the charge scalar. Here we can try to do something similar. We can try to establish some equation for these objects, and this is what I'm going to do now. So you see how I am following the steps for the charge scalar. To do that, you need to pay a price, and the price is that you need to put some coordinates or on sigma 2 on this manifold. In 2D, you can do it canonically, because in 2D you have this complex structure and you can always put complex coordinates. The point is that when you rewrite the action in coordinates, this in coordinate means this, that you put explicitly the coordinates in the action. And now, because in the previous action here, this is coordinate-free notation. There is no coordinates here. But when you rewrite the action in coordinates, see what happens. Now the constraint rewrites like this, and this means that you have left and right modes, and only one of them survive in this theory. But more important is that the scalar field only couples to a set bar, one of the components of the one form, and not the other. So there is no coupling between bar set, the derivative with respect to set bar and the one form. There is no coupling between them.
Is it same as previous one? I mean, here I don't see this G and G bar democracy. the G and G bar different. What broke this symmetry?
G and G bar, sorry. Where?
Here, I don't see any room to break G and G bar rotational symmetry. This parity symmetry.
This action
Yeah.
is exactly this one.
So where did you break G and G bar symmetry?
Yeah, when you write this in complex coordinate, because of this term, this extra term, kills one of the.
Only one.
Yes.
G and G. So that choose G over G bar.
Yes, exactly.
Yeah.
Here you can put minus if you want. No? In this case, you are describing the anti-chiral theorem. But this is for the chiral one. This is why I have this extra term here with plus. It's like changing the charge. This is now. Now
So
the
that
theory
condition, bound to Z bar phi equals 0.
This
Does it
condition.
arise from equations of motion or?
No, that's a good point. This condition is this one.
So you impose that.
No, I haven't imposed this condition. What I want.
But what I mean is round the Z bar phi equals 0. That equation, you're saying that.
That equation is this one.
Yeah, right.
Yes. But now you can see that this equation in complex coordinate looks like this.
Yeah, exactly.
That's fine.
And now you see that in the action in complex coordinate you don't have this object. I mean, there is no coupling between A and this. This is why you don't need this condition in the quantum. I mean, this action already takes into account this condition.
Oh, but then my question is, so you're saying the action written in this coordinate form,
Yes.
in the next slide,
Yes.
you didn't impose that condition yet.
No. No.
So
And I don't have to do it.
Yeah.
I don't have to do it because there is no coupling.
That's your point.
Yes. I don't have to do it because there is no coupling between the A field and setback. So this is like in this action, this condition is already satisfied.
I'm also a bit confused. Actually, it's the same question.
Yes.
Because if you impose that kind of bound Z bar phi equals 0, if you impose it,
yes,
I can understand the non-democratic expression. But because your starting expression, coordinate-free expression, has no preference to Z or Z bar, right? So if you, in this expression, if you decide to choose alternative.
No, this construction, the action, this one, you don't see it here, but it prefers, because of this sign here, plus, it prefers this form. Actually, if you change this sign, what you get you change this sign, of course. Now you are in the anti-chiral theory, so this condition will be minus here. You have to change this sign here. What you get here is
maybe
the opposite coupling.
Yeah, maybe the Hutchie star probably could reason behind.
Sorry, what?
Hutchie star is actually, seems like Z bar dependent.
Yes, yes, exactly.
Yeah, now I see.
So by choosing coordinates, now you can rewrite this in this way, and then you realize that there is no coupling with this field, and because of that, you can establish this equation. And basically, this equation is telling you that this is an holomorphic section of the line model. But we can forget this for the moment. It's not important. The important point is that we have an equation, and in addition, we have one more equation, which are the one identity. So in principle, now we have two equations, and they can be written in terms of covariant derivative. You can introduce these two objects, which are actually the components of the one form, and these two objects behave as connections for this covariant derivative. By doing this, now you can establish these two equations. Now we have three information about the partition function. We know that the partition function, when these two fields are 0, we recover the original theory. We know that it's a holomorphic section of a line bundle, but basically this is equivalent to say that there is no coupling with this. So automatically I'm taking into account this condition that I wanted to take into account. That I didn't know what to do with this. Now I know that this particular non-gauge invariant action take into account this condition. And we know that we have these two equations describing or defining the partition function. Because of that, let me recap. We don't know how to compute the original chiral theory. We don't know how to compute the partition function for the auxiliary theory. We don't know actually. But we know that now it's a holomorphic section of a line bundle. And remember what I said at the beginning, no? Let me do it here again, no? If for the scalar field, I have this equation, and I know that this scalar field transforms like this. If I find another function, it's a different transforming exactly like this. If I find another function transforming exactly like this function will be a solution of this equation. In a different gauge, but it will be a function of this equation because basically these two objects belong to the same box, the same line bundle, the same set. For a different A, no, but it's a solution in a different gauge, but the same equation. This is what I'm going to apply here. I don't know how to compute this partition function, but if I am able to find another function transforming as this line bundle, for sure it will be a solution of these two equations. And it will be physically equivalent to this, different gauge, but physically equivalent to this. And this is what the famous Witten observation. Witten did is he realized that if you take the Chern-Simons theory, this is really amazing. If you take Chern-Simons theory in one higher dimension, you take Chern-Simons theory with the usual U1 transformation, you realize that this action transforms exactly as this one, or one more as this one. It has exactly the same transformation. So applying this idea, now I can say that this new Chern-Simons, this new action, or this new partition function, see that this A1 here is the boundary value of this field. This small a lives in the A3, and the boundary value is on this sigma 2, which is the original manifold. This partition function is the one that solves these two equations. Hence, this partition function is the one that we want, and we know how to compute. In principle, we know how to compute the partition function of Chern-Simons, which is easier. It's topological. It is much easier to compute than the previous action, the previous partition function. And in addition, it contains already the condition, the duality condition that we wanted to impose, that classically we have some problem to impose. Now we know that this action already contains this information. One thing which is different from the usual Chern-Simons, and this is one of the hard part of this, that I'm not presenting this, I'm not presenting the geometric quantization of Chern-Simons, which is related with this. But one of the things is that in order to have exactly the same transformation, this constant here has to be 1/2. And this is unusual for Chern-Simons because Chern-Simons needs an integer here, not a half integer. But in this case, this can be solved just postulating or just saying that this manifold has to be a spin manifold. If you say that, this is not a problem for the theory. So by computing this partition function, you can compute the partition function of the chiral theory. And the same happens for the N5 brane. Now in a higher dimension, but with exactly with the same structure. Oh, sorry, here is 3. It's not 4, it's 3. 3, this is 4, and 3, 7. This is 3 here. So, but exactly the same structure, you can compute the partition function of the N5 brane. And it will be a chiral partition function. So this is basically the Witten's approach to this kind of partition function.
So here the real non-triviality is this very first equality, because both sides transform the same way. They must be equal. I'm not yet convinced.
Yeah, I mean, but you can read the second paper I showed at the beginning, at the introduction, which is the hard part of this, and they formally show that this is correct, with theorems, with the definition, theorem, everything.
So like transformation will uniquely fix the
Yes.
function.
Yes, exactly. This is basically the idea, and you got it. It's perfect. This is the idea. Yes, you are not convinced, but this is the idea. And this is really a very good idea. No? This is amazing. But are you convinced with this argument? Because this is an easier argument. No, if you have for the scalar field, you know that the scalar field transforming like this. If you find another field transforming like this, it will be a solution of this. Basically, it's the same. Of course, the space here is not the space of X; it's the space of connection, blah blah. But the idea is similar.
I cannot see that.
Okay.
You have a fixed gauge field A. There is A prime as well, yeah.
Yes, A is inside the covariant derivative. What I'm saying is,
You wrote down gauge transformation for only phi, yeah. There.
yeah, if you find another field,
It's about phi, different from
yeah,
phi.
it's a
Okay.
different.
Okay.
It's different. But you know that this field transforms exactly like this one, like the original one.
Okay.
This will be a solution of this equation.
Why?
Oh wait, but I
Because-
think solution. I mean, solution may, yeah, because now,
But these two are related by a transformation.
They are not related.
They belong. They are section of the same line bond.
yeah, so what I think what we're saying is that is already non-trivial statements because so what we can tell is that if we satisfy that gauge transformation,
Yes.
then we know how d phi transforms.
Yes.
It has a very nice transformation rule. We know that. But now you're talking about d phi, d dagger d phi is 0. It's a stronger state, right?
No, because I mean, if this transform like this, also the derivative also transform like this, and d dagger transform like this. What I probably the non-trivial part here is that d is d minus IQ a, no?
Yeah.
And here d is d minus IQ a prime. It's a different a. And these two A are related by the gauge transformation. And as long as the gauge transformation leave invariant.
So I don't follow your notice. You are using same D. You should put D prime in the bottom, no?
Okay, D prime here. Okay.
Why you use the same symbol D? Even after gauge transformation.
Because D is the covariant derivative. What I'm saying is.
So so maybe I can ask a question in this manner.
Okay, yes.
There's a transformation rule,
Yes.
and there is a, let's say, let me just call the equation solution.
Yes.
Usually this term different stuff, right?
Yes.
Phi, let's say, I'm gonna say this phi transform under the gauge transformation in that manner. We can just give them.
Mhm.
But it does not tell us that if this satisfies the equation solution or not. It's a different problem, right? So that's why I'm confused. So if d dagger d phi is 0,
Yes.
it's actually not about gauge transformation at all. It's just restricting the phi. It says phi satisfies some equation.
Exactly. But
Right.
what I'm saying is that now you have a different function that also transform like this. These two functions are related by a gauge transformation. There is a relation between 5 e to the q beta u1 is another 5.
Why? This is
Because they are related by the gauge transformation with a different A. But they are physically equivalent because what is physical here is F, not A. A is a connection. What is physical is
something. I mean, the top line that justify what you say, but I don't see why you have that top line equation.
Yeah, Wi-Fi is Wi-Fi are related to that. That's
Actually, I can quickly construct here a solution of this. So you will see this. I can construct this solution. And this solution, if you plug this solution here, actually you are picking a gauge which is A equals 0. This is a solution of this equation, A equals 0, in this particular gauge.
You mean actually you denote the same field by different notation, right?
Basically,
qualify,
but
yeah.
this is what I'm doing exactly.
They have the
this is
same section.
this is a different representation of the same field. Exactly. It's a different.
They have the same section space.
Yes.
Right.
Yes.
Yeah.
Exactly. But this is what.
So you just pick up a different representative here.
Exactly.
Yeah.
Let me go back here. No. This is exactly the idea. This is a different representation of the original path integral. So I'm just rewriting the path integral using this idea here.
yeah. So yeah, I think the point is that looks natural because it's scalar and we know that it's just numbers. So
Yes.
in the same class, so you can always rewrite scalar by multiplying something to scalar. It looks natural.
But it's a
Yeah.
phase vector situation. It's not arbitrarily compressible.
Yeah. So
Is it what? Sorry?
Phase vector.
Yes, the phase. It has to be actually. This is the definition of line bonded. Here you cannot put any. It has to be a
Yes.
phase.
basically something mathematically rigorous structure is hidden there for this to work. I mean, that's
Yes.
what I have.
Yes. And first, I don't have time to explain this. And second, I think I understand half of this part of this mathematical structure. But this is the idea, basically. So yeah, I am representing the original partition function just using a different.
By the way, you have 17 things.
Okay, yeah. Let me try to.
Breaking that is here.
Democratic M theory. I will try to go faster here. But first, let me introduce what is the democratic theory. This is the original formulation of, and by M theory, I mean just the supergravity, the 11-dimensional supergravity. This is the original formulation. The classical formulation is formulated in terms of A3 only. And the question is, can we, when we want to compute the observables of this theory, the same way we compute observables in the microscopic theory, we have M2 and M5 brane. And we can copy the M2 without any problem here, but if we want to copy the M5, we don't have the potential, the A6 potential here to copy with the M5 brane. This is why we want to introduce the democratic formulation. The democratic formulation, in the democratic formulation, you double the degrees of freedom, so you introduce F4 and F7 at the same time, and this object here is defined by the solution of this equation. And what you can see is that if you now impose this condition after the equation of motion, this is the classical version. We will see what happened in the quantum version, no? But in the classical version, you have to impose this condition after the equation of motion. But you see that this condition is similar to the condition of the chiral theory. No? Now we have an action, we have a chiral condition, and we want to compute the partition function of this new action. So yeah, this is the definition of the democratic theory. When you go to the literature, there are several democratic theories. This is related to your question. There are several democratic theories. Actually, you can find the one that I'm using here, which is the one that is adapted for this calculation. You can find two versions. One with these coefficients, alpha, beta, and kappa, and one with these coefficients. And you will see what happened at the end related with this coefficient. No? But in general, I will work with this kind of action, or the one that can be written in this way. And I want to compute the partition function of this action. And similarly to the previous examples, with this constraint that I don't know what to do in the quantum version with this constraint. And in advance, I can tell you that something similar to the chiral theory happens here. So now I will follow. Remember the recipe. No, there are 3 steps. The first one is I need a symmetry, but it's not any symmetry. It's a symmetry like a shift. No, I need to make a shift on the fields. This is the first step. No, but in this case, it's a p-form symmetry. It's not a 0-form symmetry. So almost from the beginning of this formulation, apart from the usual gauge transformation of M theory, there is one more symmetry which is given by this transformation, and this is the one that we need. Now you see that this is similar to the transformation of the scalar when you shift by a constant and then you relax this condition, except for this extra term here. But it can be found in this paper or in this one related with non-invertible symmetries, but this is a higher form symmetry, and it's the one that we use to relax this condition and couple with the theory with the background fields. So the second step in the recipe is to couple the theory with background field, relaxing this condition. For F4, which is the derivative of A3, is similar to the previous example. So there is no problem in just introducing this extra background field here and postulate that this background field transform like this. So now F4 with this, when you relax this condition, this is the gauge invariant combination. For F7, it's a bit more complicated, because naively you may say, okay, I can do similar thing as I did for the F4. The point is that F4 contains this extra Chern-Simons term, depending on, sorry, F7 contains this extra Chern-Simons term, depending on F4. And this is not the transformation, or this is not the coupling that we need. Because if you use this coupling, when you go to the construction of the section of the line bundle, you get that you don't get a section of a line bundle, you don't get the phase. You don't get the phase you want. This is why you need to introduce a more complicated coupling given by this term. And so this is basically the idea. The C fields they have to transform with the C fields, and not the transformation should not depend on the quantum field of the theory. Remember, this is a background, no? And these are the. If you work with this transformation, you don't get the line bond that you want. Sorry, I'm going faster. So what do we have now? We have a democratic theory. Here we have to introduce a different constant because of now I want to deform this theory, and the deformation of this theory also contains a term similar to this. This is why I have to change this number here, and I have to fix at the end of the calculation. I have this combined gauge symmetry. Now I am in a similar situation to the previous example. The question here is, what is the deformation? In the previous example, we can realize that when you have already the deformed theory, you can go to the Chern-Simons and see they transform exactly the same. Here I don't know what introduced here to deform this theory to get exactly this phase that I want. But I can take this transformation similar to what happened with Chern-Simons. In Chern-Simons, you have the same transformation in the boundary. You extend the transformation to the bulk. Here you can extend this transformation to the bulk, which, by the way, the bulk now is 12-dimensional manifold. and extend the transformation to the bulk, and then before computing the deformation of the 11-dimensional theory, you can compute the theory in 12D using this transformation. How? A plus the most general 12 form you can have. A plus B plus C or E. There are too many C's here. E. And then what you want? You don't want an invariant action. Because if you have an invariant action, you don't get the space. You want an action that transforms only in 11D. So you want a total derivative transformation, similar to Chan-Simons. So when you impose this, you get that the transformation of this action is given by this object here. And in addition, you don't want this quadratic term here. This is why you fix B A equal B with these boundary values. And at the end, what you get is this, for this choice, what you get this action. Or this action in 12D transforms like this in 11D. This action is similar to the Chan-Simons in the three-dimensional, the 2 and 3-dimensional case, or the
transformation written in 11D space matches the transformation of the democratic background field couple transaction.
This is the transformation of the 12-dimensional.
Yeah, I understand that. So the whole point of written is the variation of Chan-Simons term.
Yes.
That transformation rule just identical to the original self-theory, right?
Yes.
So does it match?
Exactly.
Yeah.
Exactly. Now I haven't found yet the deformed 11-dimensional transformation, but now I know how this action should transform, like this. And by using this, that's the idea. Guided by this transformation, I can find the 11-dimensional deformed action. And by using this action, now the combined, no, there is one more term. This is why I had to change one of the constants. But by using this action, now I can have, you see, the S0 plus the deformed action in 11D. And by computing this, I know that this object, because of this part, is gauge invariant. However, this part is not gauge invariant. This part transforms like this, which transforms exactly as the 12-dimensional action. By using this, now I know that this partition function I'm computing is the partition function using this auxiliary theory transformed as a section of a line bundle. And in addition, satisfy this.
Wait, I'm confused because
Yes.
if the variation of the SD part,
Yes.
if that matches the variation of the Chan-Simons
Yes.
variation,
Yes.
you're saying the first term S0.
Yeah, this term is gauge invariant.
It's invariant.
Yes. This term is similar to the terms in the chiral theory. No? You have a part which is gauge invariant, and then you deform the theory with a non-gauge invariant term. This is similar here. It's exactly a similar idea. But in 1 hour, I think we need more time.
So your 12-dimensional Chan-Simons partition function is independent of F0.
Yes.
In front of F0, I can put any constant. It's independent of that constant.
Yeah, it's not independent. Let me tell you, because S0 is not any action. S0 has a particular gauge symmetry. It's invariant on the particular gauge symmetry, and because you use this gauge symmetry to construct the 12-dimensional action, and then the 12-dimensional action give you the deformed action.
But I can put any constant in front of F0.
No. As you cannot put any constant in front of the chiral scalar, because otherwise you don't get the holomorphic condition. So these constants are related by this. No? It's not that you can put any constant. And I am not discussing this here, but you will see why you cannot put any constant. So now you have two equations to describing this partition function. This partition function here satisfies these two equations, and your question is consistency. Because of consistency, you get that these two constants, this one, particular this one, is the one in front of the 12-dimensional action. And this one is the one that I had to change because of there was an extra Chern-Simons term, but because of consistency, and I need 1 more hour to explain consistency, but because of consistency, these two constants are not any constant, they are related by this. And in general, now you get, did I mention that? Sorry, this is important. Yeah, this is an important point. Let me mention this before going to the end of the talk. But I got this action just by a gauge principle, using the gauge variation. However, this action was also obtained in this paper using completely different arguments, completely different motivations. You can find this action already in this paper, previous to my paper, where they find exactly this action for describing the democratic 11-dimensional supergravity in 1 dimension less. This is an important point. Yeah. So let me finish. Why you laugh?
That's why you are jumping.
Actually, no. You know the story. I can tell you the story at the end. So let me. I'm finishing. So now the calculation should be. I need to compute this partition function. I know for sure that this partition function computes the partition function of the democratic 11-dimensional supergravity. However, this partition function has these boundary values, but the democratic that I want is with this boundary value. So if I compute this partition function, this boundary value, effectively I am computing the partition function of the democratic theory. And as I told you, this guy here, this constant here, is given by this, alpha plus beta. Okay, yeah. It's given by alpha plus beta. And one funny thing, remember I told you that there are, at least I found two theories in the literature which has different alpha and beta. And in one of them, alpha is 1/3 and beta is 1/6, kappa is 0. However, alpha plus beta is 1/2. In the other version, I found it's 1/4, kappa is this. However, alpha plus beta is 1/2 again. Why? No idea. Why this action doesn't care about the choice of these coefficients. No idea. But this is a funny thing about this. So this action is computing effectively the partition function of these two theories at the same time.
So you're saying that there were two different choices of the equation
Yes.
appeared in the literature. Yes. Both can be connected to this 11 here.
Exactly.
Somehow.
Why? No, I don't know.
And both should have the same partition function.
Yeah, I mean, if you want to compute the partition function related with this action, with this choice, you get 1/2 here, or you compute this partition. If you instead want to compute the partition function with this choice, again you get 1/2 here.
Yeah, same answer.
Yes. I don't know, but this is a funny thing related with this result. So yes, I think I can stop here. Just one thing is to say that this is a section of a line bundle, and a different thing is to prove that this line bundle exists. No, in the paper, in the second paper I showed at the beginning, not the width in the second one, they show that the section, this line bundle, not the section, the line bundle for the Chern-Simons is a well-defined proper mathematical object. Here, we don't know how to do it yet. Another thing is understand the geometric quantization of the 12D theory similar to the geometric quantization of the Chern-Simons theory. Because this this is not a Chern-Simons theory, but it's a BF-like theory, because it's like a BF. We don't know, we don't understand, we don't fully understand this topological theory. And one more thing is extend, introduce the M2 and M5M, because this calculation, I did this calculation only without this object, and the main motivation, the original motivation, is compute the partition, compute the expectation value of these two objects. So we need to do this. We know how to do it. It's a bit hard, it's very difficult, but we know how to do it. And this is work in progress. We want to extend these results to the calculation of the partition function in type 2B supergravity, where we have similar problems. We have the F5 form. It's a chiral, but in addition, we want to extend to the full democratic theory, not only the 5 form, but the full democratic type 2B, and apply this work in progress. And we have almost finished this work. We have similar results to the 11-dimensional case. Yeah, let me stop here.
Good. Thank you very much for the nice talk. So we're gonna have Q&A session now. So just please ask him about any questions, including on Zoom.
So, yeah. So
Please.
you are using Euclidean signature.
Yes, it's Euclidean. Yeah, I didn't say that, but it's Euclidean partition function, yes.
So when you, then the question is the path integral measure, is it real line integral or complex integral now? Because your self-duality involves I. So.
Yeah, that's good. These fields are complex. Yeah, when you go to the Euclidean version, because of, as you said, there is an I in the duality constraint. Now these fields are complex.
But
Similar.
integral is complex.
Yeah, you are integrating.
Line or complex plane. That's my question for the path integral.
It's a complex infinite dimensional plane. Yes, in the space of connections. Yes, that is complex. Yes, but in type 2B, something similar happens. No? When you compute the partition function, or you evaluate the action, which is similar to what you did, the 5 form is complex. It's not real. It's a complex object.
But I'm pretty sure that one actually knows how to do genuine mathematically rigorous path integral field, right? I mean,
yes, exactly. No, this is formal. This is
formal.
In 2D, for the chiral scalar, it's more than formal. No? I mean, it has been proven that with theorems, with definition, with all these steps, no, that you can compute, you can do this calculation without any problem. In this case, no, I don't really know how to do it, or how to formalize this mathematically.
So, you know, there are alternative actions which automatically take care of the self-duality by its own equation model.
Yes, I know.
Do you see there the partition function of those actions will agree with what you get?
Actually, one thing is this, and I want to say this very careful now. These other actions are not good for quantization. They are not. In the end, I will show you the last version of my paper that finally was accepted for publication. After several discussions with the referee, I end up saying that they are impractical for quantization. The referee agreed in that. So this is why I didn't use this action, no? Because they are good for classical theory or for evaluating the path integral, but when you want to do this kind of calculation, you don't know how to properly define the path integral. One more thing, no? If you get this condition as an equation of motion, I cannot apply this Witten idea, because this Witten idea relies that you have this extra self-duality constraint, and then you translate this self-duality constraint to a holomorphic condition, the quantum level. This is why I need this extra constraint as a constraint, not as an equation of motion.